Welcome back to the video course on fluid mechanics. So, in the last lecture in the kinematics of fluid flow, we were discussing about the basic potential flows. We have seen the uniform flow, the various aspects of uniform flow, source and sink, and also vortex. So, in vortex we have seen that say here say flow in which the streamlines are concentric circles, and then as far as vortex is concerned, it can be say either rotational vortex or irrotational vortex. So, as mentioned, rotational vortex is a free vortex. Say for example, the motion of a liquid contained in a tank that is rotated about its axis with an angular velocity omega. That is an example for rotational vortex, and in the case of rotational vortex, it is also called as free vortex. Say for example, the sailing motion of the water as it drains from a bathtub is an example of rotational vortex. And then there can be also combined vortex. So, forced vortex has a central core and a velocity distribution corresponding to that of a free vortex outside the core can be described as a combined vortex. So, out of this mainly in potential flow we will be dealing with the rotational vortex, and rotational vortex is the one of the basic potential flow. So, now say with respect to this vortex, say another important parameter is called circulation, which we have already discussed earlier. So, here in this slide you can see that circulation gamma, say capital gamma, it is a line integral of the tangential component of the velocity taken around a closed curve in the flow field. So, here you can see that here there is a closed curve, and then the circulation is defined as the line integral of the tangential component of this velocity. Here you can see this velocity here, and then it is taken around a closed curve. So, circulation can be say described, gamma is equal to this integral v ds. So, where c is the closed curve which we are described here, and then as far as for irrotational flow is concerned, this gamma is equal to say gamma integral c d phi is equal to 0. So, that is for irrotational flow which we are describing here, and it shows that for irrotational flow circulation is 0. So, say we have seen that the vortex can be forced vortex or the rotational vortex, say which we have seen rotational vortex or forced vortex and free vortex. So, out of this rotational vortex means say circulation is 0. So, it shows that for the rotational circulation is 0, but if there are singularities enclosed within the curve, circulation may not be 0. So, within the curve, if there is a singularity occurs, then we can see that this circulation may not be 0. So, irrotational vortex also, if there is a singularity in the curve within the curve, then there is a possibility that circulation may not be 0. But generally for irrotational vortex or say free vortex, say the circulation is equal to 0. So, the circulation is an important parameter which we use as far as vortex is concerned, say as far as rotational vortex or irrotational vortex is concerned. And then we have also defined the tangential velocity for the vortex as v theta is equal to omega or v theta is equal to k by r when r is greater than r0. So, as described earlier. So, now say for example, if you consider the circulation, so here you can see in this figure, say with respect to the velocity v theta, and then with respect to the radius r, here this theta is mentioned. So, for example, for the free vortex with v theta is equal to k by r, circular path of radius r can be described gamma is equal to integral 0 to 2 pi k by r d theta, or that is equal to 2 pi k. So, here for free vortex we can see that circulation, say within this, as we can see that here we can consider singularity inside with respect to the vortex, and then gamma is equal to 2 pi k. So, circulation around any path without a singular point at origin will be 0, and here if there is a singular point as at origin here, so that it will be gamma is equal to circulation is equal to 2 pi k. So, the numerical value of the circulation depends upon a particular closed path considered. So, as you can see here, whether there is a value for the circulation or the circulation is 0 depends upon within the closed curve there is a singularity or not. And so here if it is there as shown in this figure, so gamma is equal to 2 pi k, otherwise the circulation around any path without a single point at origin will be 0. So the circulation is also an important factor which we should consider as far as when we consider the vortex flow in potential flow theory. So we have to see that whether there is the circulation is equal to 0 or circulation has got some value depending upon whether there is a singular point within the circulation. So finally, for free vortex we can write the potential function phi is equal to, so with respect to this the circulation parameter which we have shown here gamma. So with respect to this we can write this phi is equal to the potential, the velocity potential phi is equal to gamma divided by 2 pi into theta. So with respect to the previous figure, say if we consider this theta here, and then we can say that the velocity potential phi is equal to gamma by 2 pi is equal to 2 pi theta, and then the stream function psi is equal to minus gamma 2 pi natural log r. So for a free vortex flow with respect to if there is the circulation gamma, then we can define the potential velocity potential phi is equal to gamma divided by 2 pi theta, and then psi the stream function is equal to minus gamma by 2 pi natural log r, where gamma is the circulation and r is defined here and as well as in the previous here. So with respect to this figure here you can see r is defined, theta is defined, and then so with respect to this figure here, say we have already seen earlier the general definition of phi and psi with respect to phi is equal to k theta and psi is equal to minus k natural log r. With respect to the circulation gamma, we can define this say for the free vortex phi is equal to, for free vortex phi the potential velocity potential is equal to gamma by 2 pi theta, and psi, say stream function psi is equal to minus gamma by 2 pi natural log r. Another important the elementary potential flow, basic potential flow is called doublet. So now we have already seen the uniform flow, then we have seen source, sink, and also we have seen the vortex. Now we will see the last one in this elementary basic flow, elementary potential flow called doublet. So now say the doublet is formed by combining a source and sink in a special way of equal strength m. If there is a source of strength m and if there is a sink of strength m, then we can get a doublet when we say put it in a or combine the source and sink in a particular way. So here with respect to this slide here you can see that how a doublet is formed. Here there is a source of strength m and here there is a sink of strength m, and then here this is the origin, and now the source and sinks are separated by a distance a on the left hand side and a on right hand side. So here the r is defined with respect to point P, the r is defined r2 and r1 with respect to source and sink, and angle theta 1, theta 2 and theta are also defined here. So x axis in this direction, y axis in this direction. So here with respect to this equal and opposite, that means since it is placed in the opposite direction with respect to this equal and opposite or equal strength source and sink, a doublet is formed when this a, this distance a tends to 0 and then this comes to very nearby. So a doublet is formed with respect to a source and sink placed at a distance, and when that distance tends to 0, that means the source and sink tends to come to this origin the same point. So then we say that a doublet is formed. So further we will see the different aspects of this doublet. So now here the strength of the source or sink we have already seen with respect to the definition, psi is equal to minus m by 2 pi theta 1 minus theta 2. So with respect to this figure theta 1 theta 2 are defined here. So with respect to this figure, the stream function we can define minus pi by 2 pi into theta 1 minus theta 2. So then say this with respect to this figure, again we can define tan minus 2 pi psi by m can be defined, this is equal to tan theta 1 minus theta 2. So, that is equal to tan theta 1 minus tan theta 2 divided by 1 plus tan theta 1 tan theta 2. So, here theta 1, theta 2 and theta are defined with respect to the figure here. So, now we say that with respect to this previous figure, here tan minus 2 pi psi divided by m is equal to tan theta 1 minus theta 2 and that is equal to tan theta 1 minus tan theta 2 divided by, when we expand this, divided by 1 plus tan theta 1 tan theta 2. So, tan theta 1 with respect to the previous figure, we can write tan theta 1 is equal to, here tan theta 1 is equal to r sin theta r divided by r cos theta minus a. So, here it is obvious, r sin theta, r is defined here, r sin theta divided by r cos theta minus a, and tan theta 2 is defined as r sin theta divided by r cos theta plus a. So, here with respect to this figure, all these parameters are defined, and then this tan minus 2 pi psi by m can be with respect to this tan theta 1 and tan theta 2 defined here, we can write this is equal to 2 ar sin theta divided by r square minus a square, and when as the definition of the doublet is when this a tends to 0. So, when this a for small a, we can write psi is equal to minus m divided by 2 pi 2 ar sin theta divided by r square minus a square. So, this is equal to minus m by pi ar sin theta divided by r square minus a square. So, now the doublet, we will say that a doublet is formed letting the source and sink approach one another. So, here there is a source say with respect to the figure shown there. So, here if this is the origin and this is y, this is x. So, here there is a source and here there is a sink, here there is a source. So, when these two reaches, that means is this initially the distance is a here on both sides. So, when this a tends to 0, letting source and this source and sink approach one another. So, that a tends to 0, then we say that while increasing the strength of m is going the strength of this source or sink, m is the strength of the source or sink. So, when m tends to infinity and a tends to 0, we say that a doublet is formed. So, that we can say that the product m a by pi remains constant. So, this is obvious from this figure. So, here the source or strength, its source and sink strength m, that is tending to infinity, going becoming large, and then this a tends to 0, so that it approaches this origin. Then we say that a doublet is formed, and so that the product m a by pi remains constant. So, m is the strength and a is the distance between from the origin to sink or source as described in the previous figure. So, that m a by pi remains constant. So, from the previous equations here as in this slide, the previous slide. So, here this r by, so that when a tends to 0, we can say that r by r square minus a square is tending to 1 by r, or finally a stream function psi is equal to minus k sin theta by r, where k is a constant which is equal to m a by pi. So, this m a by pi is called the strength of doublet. So, the m which is defined as the strength of the source or sink. Now, say the doublet, for the doublet which we consider, the strength is defined as this, the constant k which is equal to m a by pi is called the strength of the doublet. And finally, the velocity potential is with respect to this, we can write phi is equal to k cos theta by r as per the definition shown here. So, the phi, finally the velocity potential phi, we can define phi is equal to k cos theta by r. So, you can see that when it with respect to this slide, as the previous slide, when it approaches this source and sink approaches to the origin. So, it is represented here, you can see that the both the source and sink approaches and then to the origin. So, that the doublet streamlines are plotted like this. So, finally, we can say that a doublet is formed by superimposing a source and a sink along the x axis like this, and the doublet is commonly used as one of the fundamental singularities. So, the as defined in this figure, the doublet is formed by superimposing a source and a sink along the x-axis, and then we can say that this is one of the fundamental singularities, and also for the velocity potential for a doublet is defined as phi is equal to k cos theta by r, where k is called the strength of the doublet, which is equal to m a by pi, where m is the strength of the source or sink, and a is the initial distance which we defined in this figure. So, this is the definition of the doublet, and the various parameters are also discussed. So, finally, the doublet is just as a source or sink are not physically realistic entities, also the doublets are not physically realistic entities. So, we are just assuming these kinds of entities so that we can define many other complex flows. So, combined with other basic potential flow provide useful representation of flow field. So, which when we discuss just now after this we will be discussing about the combination of these basic flows, then we will see that how this doublet is useful for further representation of the complex flows. So, for example, combination of a uniform flow and doublet gives the flow around a circular cylinder. So, circular cylinder, the flow around a circular cylinder is very important, and we have to determine the streamlines, potential lines, and various parameters as far as flow around a circular cylinder is concerned. So, to define various parameters, we can use this doublet, and when a doublet is superimposed with respect to uniform flow, we will get the flow around a circular cylinder. So, even though the source sink or source sinks or the doublets are just are not physically realistic entities, but we can say that this assumed or the unrealistic entities we can define in such a way that finally this source or sink or doublets can be superimposed with the uniform flow or other flows, and finally we will get various other types of complex flows, which is very useful, and we can easily define various parameters for example flow around a circular cylinder. So, now with respect to these definitions, finally we will summarize here the summary of elementary flows. So, in this slide we can see that say here now so far we have discussed the uniform flow, source and sink, free vortex, and then the doublet. So, as per the definitions which we have seen so far, for uniform flow we define the velocity potential phi is equal to u into x cos alpha plus y sin alpha in the Cartesian coordinate, and psi is equal to u into y cos alpha minus x sin alpha, and the velocity components we have defined u in x direction as u cos alpha and v in the y direction as u sin alpha. So, similarly for source and or sink we have defined the velocity potential phi is equal to m by 2 pi natural log r, and psi is equal to m by 2 pi theta, and v r the radial velocity is equal to m by 2 pi r, and v theta is equal to 0 for source or sink, and it is said to be a source when m is greater than 0 and m is less than 0, we say it is a sink. And then we have seen the free vortex. So, free vortex is concerned, we can say that the velocity potential phi is equal to gamma the circulation by 2 pi theta into theta, and psi is equal to minus gamma 2 pi natural log r, and the radial velocity v r is equal to 0, and v theta is equal to gamma by 2 pi r, and we say that when gamma for free vortex this parameter gamma, say which we have already defined earlier. So, here we have already defined earlier the circulation gamma. So, the circulation is defined here. So, with respect to this circulation, when circulation is greater than 0, we say that it is counterclockwise motion, and when circulation is less than 0, we say that means it is negative, we say that there is clockwise motion. And finally, we have seen the doublet. Doublet is for doublet the velocity potential we have defined phi is equal to k cos theta by r, where k is the strength length of the doublet, and psi is equal to minus k sin theta by r, and then we have defined the radial velocity Vr is equal to minus k cos theta r square, and V theta the tangential velocity is equal to minus k sin theta by r square, and then we can define various other parameters u v in x y direction and V theta Vr with respect to the basic definition which we have already seen earlier. So now further, so we have now seen for 4 different types of elementary flows: uniform flow, source or sink, and then free vortex, and then doublet. So 4 elementary flows we have seen, 4 elementary potential flows we have seen. So with respect to now, we are going to say superpose some of these elementary flows, so that we will get to some we can define some of the complex flows. So this we will discuss in the next few slides. So superposition, next topic is the superposition of elementary flows. So as I mentioned, so varieties of flows can be constructed by superposing the elementary flows patterns like uniform flow, source, sink or doublet, and vortex. So potential flows produce body shapes with lift but predict zero drag. So this is another disadvantage of this potential flow theory when we compare with the realistic fluids, real fluids. So for potential fluids or potential flow, we are assuming that the viscosity is negligible, so that the potential flow are defined accordingly. So then with respect to this, all this definition, we can see that always the drag is predicted 0, which is not realistic for real fluid. So this is one of the limitation of this potential flow theory. So anyway, this further we will discuss, and potential flow solution gives mainly the velocity field, and then we can determine the pressure from the Bernoulli's equation. So with respect to the basic potential flows of uniform flow, the vortex, source or sink or doublet, we can define many of the complex flows, but only the limitations is that say since the viscosity is neglected for potential flow, we cannot predict the drag, and mainly the potential flow solution is used to get the velocity field, and after this velocity field is obtained, further we can use the Bernoulli's equation to get the pressure field for the flow concern. So now we will discuss few of the superposed elementary flows of the potential flows, then to define how we will be defining some of the complex flows with respect to this elementary flows. So as far as superposition of these elementary potential flows are concerned, there are 2 methods of combining the elementary flows. First one is called the direct method. So in the direct method, the elementary flows are combined to find the streamline pattern, the body shape, the velocity field, stagnation point, and pressure distribution. So say we can directly, it is a direct method, we are directly superposing the various parameters like a stream function and potential function in the first method called the direct method. So the elementary flows are combined so that you will get a streamline pattern, and then body shape also, and velocity, and all other parameters. So this direct method is most commonly used, and the second method of superposition is called the inverse method. So in this inverse method, what we are doing is say we will calculate the body shape to produce the desired pressure distribution. So initially we can assume with respect to the pressure distribution, so we will try to produce the pressure distribution and through the calculation of the body shape, and then it is an inverse process, and then the distinguished singularities like vortices, sources, and sinks located on the axis in the presence of an onset flow are used to determine the streamlines. So first we will determine the pressure distribution, and then from then we will be determining with respect to singularities of vortices, sources, and sinks, we will be determining the streamline. So that is why it is called the inverse method. And generally in all these methods, both the direct and inverse method, so if resultant boundary surface meets the requirements, desired solution has been arrived. So with respect to these methodologies, we say that the resultant boundary surface meets the requirements of the particular problem, then we say that the desired solution has been arrived. So this is as far as superposition of the elementary potential flows are concerned, two methodologies. One is direct method, second one is the inverse method. So, but mostly we will be using the direct method for the 2 or 3 complex flows which we will be discussing here. So, as far as superposition process is concerned, we can say that this elementary flows which we have defined, the uniform flow source or sink or the vortex or the doublet, say these are acting as just like building blocks, so that we can put one over another and then we can have the finally the complex flow. So, for example, here with respect to the Laplace equation, if psi 1 and psi 2 satisfy the Laplace equation, that means two stream function is psi 1 and psi 2 satisfy the Laplace equation. So, when we add these stream function psi 2 and psi 1 or psi 1 and psi 2, so that you will get another stream function psi 3. So, that this also should satisfy the Laplace equation. So, this is the basic principle of this superposition, and then since there is no flow across a streamline and the streamlines contain, we can say that can be imagined to represent a solid surface. So, then the Laplace equation is once satisfied with respect to two stream function, then we can say that its combination, whether it is adding or deducting, or its combination also also satisfies the Laplace equation. So, that is the basic principle that based upon which we are doing the superposition process. And then finally, we also use the streamlines which contain the flow can be imagined to represent a solid surface, so that there is no flow across a streamline. So, now we will be discussing with respect to the superposition theories discussed here. We will be discussing 3 examples of superposed potential flow. First one is a half body, second one is Rankine flow, and the third one is in the flow surrounding a circular cylinder. So, first we will be discussing the half body. We can say that say when a source in a uniform stream is superposed, we get a half body. So, here with respect to this figure, you can see that here we have a uniform flow of velocity, say u0. So, the flow is in this direction, and then we superpose a source. So, here you can see that there is a source here in the, say here x axis in this direction, y axis in this direction. So, at the origin we keep a source here. So, at any point this r is defined with respect to theta, r is here, theta is here. So, now we superimpose this uniform flow and the source here as shown in this slide here. So, then we can see that say with respect to this, a half body will be formed. So, now for the further calculation purpose, we have to change the coordinate system for the uniform flow. The uniform flow, the coordinate system which we have seen earlier was with respect to Cartesian coordinate system, that we can convert to the polar coordinate system of with respect to r and theta. So, here the string function and velocity potential law for the uniform flow are changed to the Cartesian coordinates. So, the Cartesian coordinates phi is equal to u into x cos alpha plus y sin alpha, and psi is equal to u into y cos alpha minus x sin alpha. So, here if alpha is equal to 0 with respect to the previous figure, then we can say that phi is equal to ux, that is equal to ur cos theta, and psi is equal to uy ur sin theta. So, first we do this coordinate change, and then the half body, say we can get the potential, velocity potential and stream function for the half body. So, the half body is obtained by superimposing a source in a uniform flow field as described here in this figure, and then say finally since source is superimposed over a uniform flow, we can say that with respect to the superimposition principle, we can write the potential function phi is equal to u r cos theta plus m by 2 pi natural log r. This u r cos theta is the term coming from the uniform flow, and m by 2 pi natural log r is coming from the source which we consider. And then the stream function for the uniform flow for psi is equal to psi for the half body is obtained, psi is equal to psi uniform flow plus psi source. So psi uniform flow is u r sin theta. So total psi is equal to u r sin theta plus m by 2 pi theta, where m by 2 pi theta is the psi for the stream function for the source. So finally, with respect to this superimposition of the source over the uniform flow, finally we have defined the velocity potential and the stream function like this. The velocity potential is u r cos theta plus m by 2 pi natural log r, and the stream function is equal to u r sin theta plus m by 2 pi theta. So now when we superimpose, here you can see in this slide. So say here this is a uniform flow is coming, and here the source is there, source is here, source, this is the source, and then you can see that if you draw the say the streamline, so due to the effect of this source here, the source here, then the streamlines will be the uniform flow streamlines will be deflected both ways like this, and then here with respect to the source, here the streamlines is coming to this point to the source from there, and then say finally we will get the half body here like this. So here this is the just like a solid surface, this streamline which is closed streamline here like this. So that is why it is called a half body, and then you can see that there is a point where the velocity will be 0. That point is called the stagnation point, and so here, so on the surface of this half body, the psi is equal to pi b u, where pi b is defined this the width of this half body with respect to both direction, both the upward and downward. So now for the half body which we are already defined, which we are discussed, we are mainly interested in the location of the stagnation point. So here in the previous slide you can see that there is a stagnation point where the velocity is 0. So we have already defined for the half body the velocity potential phi is equal to u r cos theta plus m by 2 pi natural log r, and psi is u r sin theta plus m by 2 pi theta, which we have already defined with respect to the previous slide. So now since for stagnation point, here with respect to this figure you can see that the stagnation point is at theta is equal to 2 pi if the origin is, say the source is at the origin, so it is at theta is equal to pi. So that the velocity component for the half body which we have defined here, the velocity components which we have the Vr, at this point, that means the stagnation point Vr is equal to 0, that means the radial velocity is equal to 0. Vr is defined as u cos theta plus m by 2 pi r. So if you equate this to 0, so Vr is equal to u cos theta plus m by 2 pi r, this is equal to 0. So at theta is equal to pi, you can see that this is equal to minus u plus m by 2 pi r is equal to 0, or we get this r stagnation which is equal to b is equal to m by 2 pi u. So this b which is defined here, the stagnation point position b, here you can see b is defined here. So with respect to this, b is equal to m by 2 pi u, where m is the strength of the source and u is the capital U is the velocity of the uniform flow. So this is the position of the stagnation point. So and also we can define the shape of the half body by following the streamline from the stagnation point. So from following the with respect to this figure, if we follow the stagnation point, and then we can track down the shape of the half body, we can follow the streamline from the stagnation point. So the value of the stream function on the streamline is, say psi is equal to u r sin theta plus m by 2 pi theta, but at the stagnation point theta is equal to pi, so that we get psi is equal to m by 2. So on this the surface of this the streamline, so here you can see that the psi is defined as pi by bu, or finally we get psi is equal to m by 2. So that is at with respect to the half body, the say the value of the stream function on the streamline of the half body on the surface is obtained, psi is equal to m by 2. And then further we can analyze, further analysis used to locate the stagnation point. We have already defined b is equal to m by 2 pi u, or m by 2 is equal to pi b u, or that is equal to the stream function. So at any point on the streamline on the edge of the half body, we can write so psi is equal to u r sin theta plus m by 2 pi theta, and that is psi is already defined pi b u. So pi b u is equal to u r sin theta plus b u theta, or finally with respect to this we can define r is equal to b into pi minus theta by sin theta. So now with respect to all this definition, we have defined various parameters, and finally for the half body Vr, the radial velocity Vr is equal to 1 by r del psi by del theta, that is equal to u cos theta plus m by 2 pi r, and v theta is equal to minus del psi by del r is equal to minus u sin theta, and the resultant velocity is equal to v square is equal to vr square plus v theta square, that is obtained as u square plus u m cos theta by pi r plus pi m by 2 pi r all square. So this gives all the parameters as far as the half body is concerned. So with respect to this discussion, we can say that if you replace the streamline with a solid boundary, so described above, this describe the flow around a streamlined body placed in a uniform flow. So the body open at the downstream end, and then this is the which is so called the half body. So as shown in this here, this is so called the half body. So we can plot this streamline with respect to the half body shape. So this is the still image showing flow around a half body, which we have already discussed. So a half body is obtained by superposing a source in a uniform flow, and then we have already defined the velocity potential, the stream function, and the radial velocity and the tangential velocity, and we have seen the stagnation point, and also we have seen how all these parameters are derived with respect to the discussion on this half body. So finally, if you want to determine the pressure at any point, we can use the Bernoulli's equation as I mentioned earlier. So the Bernoulli's equation, with respect to Bernoulli's equation, we can write the P0 plus half rho u square is equal to P plus half rho v square. So where P0 is the pressure for upstream of the half body, and u is the uniform flow velocity, v is the velocity at any point which we have calculated. Here we have already calculated v here, and then this rho is the density, and so from this equation we can get the pressure at any point. So this P gives the pressure at any point. All other parameters are already defined with respect to the earlier discussion. So to determine the pressure at any point on a half body, we can use the Bernoulli's equation as discussed here. So now finally we have already defined here all these parameters. So say some of the uses as far as the half body is concerned, we can get useful information about flows around front part of a streamlined body, such as a bridge or pier, as say here front part of a pier, streamlined body such as bridge or pier. That this the concept of half body can be used. So it provides useful information about flow around a front part of a streamlined body, such as a bridge pier or a strut placed in a uniform stream. So only the main limitation here is velocity is tangent to the surface of body is not zero realistic, that is fluid slips by the boundary. So the consequences of this assumption is consequence of neglecting the viscosity. This fluid slips by the boundary, and the potential flow differs from the real fluid, so do not accurately represent near the boundary. So only wherever the near the boundary, these theories are not valid, but beyond that we can definitely use this potential flow theory and this half body concept, which is say we can to find these streamlines or the flow surrounding a bridge pier or a strut placed in a uniform flow. We can use this concept of the half body. So that is about the half body. So secondly, we will see another concept of so-called Rankine's ovals. So, this is also by superposition of two types of elementary potential flows. So, here the Rankine ovals is obtained by combination of a source and sink of equal strength with a uniform flow. So, the half body we obtained by superimposition of a source within a uniform flow, but now we will get the Rankine ovals by superimposing or by combination of source and sink, not only source as in the case of half body, but Rankine ovals is obtained by superimposing or combination of source and sink of equal strength with a uniform flow. So, here if streamlines are plotted, the streamlines you can see that psi is equal to 0 forms a closed boundary as shown in the next figure. Here you can see a closed boundary is formed as in the case of this so called Rankine ovals. So, that is the stream function is equal to 0, and then say the streamline support streamline psi is equal to 0 forms a closed boundary, and since body is closed, all flow emanating from the source flows into the sink. So, this bodies having an oval shape is so called Rankine oval. So, a Rankine oval is obtained by combination of source and sink of equal strength superimposing in within a uniform flow. So, Rankine finally by superimposition. So, here you can see that there is a source here and there is a sink here. So, then there is a uniform flow of velocity u. So, a Rankine oval is obtained by superimposition of this source and sink of equal strength at a distance a, like in this figure, and finally the shape will be of this Rankine ovals. So, here this is so called Rankine oval. Now, as we discussed in the case of half body, so we will here also we will discuss the various parameters just like stream function and then the potential velocity potential function. So, stream function with respect to the definition of the Rankine ovals which we have seen, the stream function for Rankine oval can be defined psi is equal to u r sin theta, which corresponds to the uniform flow, u r sin theta minus m by 2 pi theta 1 minus theta 2, and the velocity potential is defined as phi is equal to u r cos theta minus m by 2 pi natural log r 1 minus natural log r 2. So, this u r cos theta or u r sin theta, this represents for the uniform flow and this represents for the source or sink which is superimposed in this source and sink superimposed in the uniform flow. So, with respect to the figure below, so here as I mentioned, here we are superimposing or we are combining the source and sink of equal strength and with respect to the uniform flow. So, with respect to this, so we can for source sink pair, the stream function can also be expressed psi is equal to u r sin theta minus m by 2 pi tan inverse 2 a r sin theta by r square minus a square with respect to this figure here and earlier definitions, and then finally psi is equal to u y, if we represent r sin theta as y, u y minus m by 2 pi tan inverse 2 a y by x square plus y square minus a square. This is with respect to the Cartesian coordinate system and this is with respect to the polar coordinate system. So, with respect to this figure finally we will get we have already defined here the potential function, the velocity potential and stream function. So, finally we get the Rankine ovals as shown in this figure. There are two stagnation points, as we have seen the half body there is only one stagnation point. Here you can see there are two stagnation point as shown in this figure, and then it is say to the distance from the center line from the origin to this stagnation point is L here, and both direction L and L, and here the thickness so this is the width of the Rankine oval. So, this is defined as h here on above and below the x axis. So, now the stagnation points with respect to where the uniform velocity, source velocity and sink velocity all combine to give zero velocity. So, for Rankine ovals, stagnation point is where the uniform velocity, source velocity and sink velocity all combines to give zero velocity. So, with this we can found by equating the resultant velocity to 0. So, so that we can find this body half length L, value of x that gives v is equal to 0 when y is equal to 0. So, when the value of x that gives v is equal to 0, since we are defining this L here with respect to the stagnation point, so where the velocity is 0. So, when y is equal to 0, so we will get this L is equal to m a by pi u plus a square its square root, and L by a, the ratio of this L and a, that means L is here and a is to the distance from the origin to the source and sink. So, with respect to this L by a ratio is obtained as m by pi u a plus 1 its square root. So, that gives the ratio of L by a, and L is defined by m by pi u plus a square its square root. So, now the width of half body, as we have seen here in this figure, the width of the half body we can be obtained from the value of y with the psi is equal to 0. So, here you can see this psi is equal to 0 is the width of the half body. So, that from with respect to the definition of the stream function we can get h, and when x is equal to 0. So, this h is equal to x square minus a square by 2a tan 2 pi uh by m from the previous definitions, and then h by a ratio we can obtain as h by a is equal to half of h by a whole square minus 1 tan of 2 pi ua by m h by a. So, here h by a is obtained by trial and error, since you can see that it is a complex equation. So, direct solution is not possible. So, trial and error solution of the equation gives h by a ratio. So, like this, say another concept, just we have seen half body. So, in a very similar way, so Rankine oval is obtained by superimposition of a source and sink of equal strength at a distance a within a uniform flow. So, this is so called Rankine oval. So, this is also we can, it is another way of combination of simple elementary flows to get a complex flow system. And lastly, here we will discuss another kind of combination of say elementary flows to get a complex flow. Here we will discuss the third case, flow past a circular cylinder. So, here the flow past a circular cylinder we can generate by superimposing or superposing a doublet with a uniform flow. So, we have already seen what is a doublet, a source of source and sink placed at a distance a is when that distance is tending to 0, and strength of source and sink is increasing. So, that is so called doublet which we have defined. So, flow past a circular cylinder is one of the important problem which will be discussed in fluid mechanics always. So, a flow past a circular cylinder can be many of the flow parameters, many of the fluid properties or flow properties can be defined with respect to this combination of a doublet and a uniform flow. So, flow past a circular cylinder is created or generated by superposing a doublet with a uniform flow. So, when distance between a source sink pair approaches to 0, the shape of Rankine oval becomes more blunt and approaches a circular shape. So, with respect to this Rankine oval itself, so you can see that when this reaches, that means this the source and strength is approaches, this A is reduced, so that it reaches a single point here, so that a blunt body is formed, and then say the pair approaches 0, the shape of Rankine oval becomes more blunt and approaches a circular shape. So, with respect to this, the definition of the doublet and uniform flow, we can define for a flow past a circular cylinder the stream function as u r sin theta minus k sin theta by r, and the velocity potential can be defined as phi is equal to u r cos theta plus k cos theta by r. So, here this figure shows the flow past a circular cylinder. So, here you can see that this is a combination of the doublet and uniform flow coming here, and a doublet as defined earlier. So, that gives the flow past a circular cylinder, and then finally next we will define all other properties as far as flow past circular cylinder. So, to obtain the stream function represents flow around a circular cylinder where psi is equal to constant for r is equal to the radius of cylinder. So, here r is equal to the radius of cylinder, r is equal to a. So, say when r is equal to a, psi is constant. So, psi we can write psi is equal to u minus k by r square r sin theta with respect to the previous definition. So, here say psi is already defined u r sin theta minus k sin theta by r. So, with respect to this, when we put r is equal to a, we can get the stream function psi is equal to u minus k by r square r sin theta. So, now we can obtain, say, for psi is equal to 0, that means here with respect to this figure on this on the surface of the circular cylinder, the stream function can be defined as 0. So, psi is equal to 0, you can see that say for r is equal to a, we can define u minus k by a square is equal to so now in this equation r is equal to a, so that u minus k by a square is equal to 0 for r is equal to a. So, now therefore, the stream function and potential function can be written as, say, as far as flow past circular cylinder is concerned, the stream function and potential function can be written as psi is equal to u r into 1 minus a square by r square sin theta, and the velocity potential phi is equal to u r into 1 plus a square by r square cos theta. So, with respect to the previous discussion, finally we got the here say with respect to the psi and phi, finally with respect to the flow past circular cylinder when r tends to a, finally we got where psi is equal to 0, r is equal to a, and we got u minus k by a square is equal to 0, or we get psi is equal to, finally psi is equal to u r into 1 minus a square r square sin theta, and the velocity potential phi is equal to u r into 1 plus a square by r square cos theta. So, now the velocity components with respect to this phi and psi, we can define the velocity component, the radial velocity and the tangential velocity can be defined. So, the radial velocity V r is, as per definition, V r is equal to del psi by del r, or del phi by del r is equal to 1 by r del psi by del theta. So, with respect to phi or psi, we can define V r is equal to del phi by del r, that is equal to 1 by r del psi by del theta, that is equal to, with when we differentiate this here, we will get u into 1 minus r square, 1 minus a square by r square into cos theta. So, this gives the radial velocity as far as flow past a circular cylinder is concerned, and the tangential velocity is defined as V theta is equal to 1 by r del phi by del theta, or that is equal to minus del psi by del r. So, with respect to this definition, if you differentiate this psi or phi, we get V theta is equal to minus u into 1 plus a square by r square sin theta. So, the tangential velocity is defined V theta is equal to minus u into 1 plus a square by r square sin theta, and the radial velocity for the flow past circular cylinder is defined as V r is equal to u into 1 minus a square by r square cos theta. So, the maximum velocity occurs on a surface of cylinder at r is equal to a, where theta is equal to plus or minus pi by 2 as shown in this figure. The maximum velocity when theta is equal to pi by 2, that means either here or this location. So, this we can obtain here when we put theta is equal to plus or minus pi by 2 at r is equal to a. So, then V r, the radial velocity will be equal to 0, and V theta s, that means on the surface of the cylinder, V theta s will be minus 2 u sin theta. So, now with respect to this figure here, we get the maximum velocity on surface is when r is equal to a and theta is plus or minus pi by 2, and that values will be, radial velocity will be 0, and then the surface velocity that with respect to tangential, the V theta is equal to minus 2 u sin theta, where u is the uniform flow velocity. And here also for flow past circular cylinder also, we can obtain the pressure distribution from the Bernoulli's equation. So, the Bernoulli's equation as defined here, Bernoulli, say with respect to the here with respect to the previous figure here, we can apply the Bernoulli's equation here. So, that we can write P 0 plus half rho u square is equal to P s plus half rho V theta s square, where the V theta is already defined here. So, where P 0 is the pressure far from the cylinder, that means much earlier, so much beyond the position of the cylinder. So P0 is the pressure far from the cylinder, and U is the velocity far from cylinder, which is the uniform flow velocity, and PS is the surface pressure. So PS, we can obtain PS is equal to P0 plus half rho U square into 1 minus 4 sine square theta s. It's 1 minus 4 sine square theta. With respect to the definition here, we have already defined V theta is equal to minus 2 U sine theta. So the pressure or the surface pressure of this cylinder PS is equal to P0 plus half rho U square into 1 minus 4 sine square theta. So we got the expression for the tangential velocity, radial velocity. We got the expression for the pressure from the using the Bernoulli's equation, and also we got the expression for the stream function and the velocity potential. So all the parameters are defined, so that the flow past a circular cylinder we can define appropriately as with respect to all these parameters. So further we will discuss some more aspects about this flow past a circular cylinder, and then we will solve a few examples for the superposition of flows in the next lecture before going to the fluid dynamics in the coming lectures.